Okay, I guess we can get started. Do you guys have any questions on anything before we get going? Jessie mentioned that she tried to log into the Canvas page and couldn't, and I think that's because I never published it because I don't plan on using it. So just stick with the web page and everything will be fine. If you ever have issues about where you stand in class grade-wise, just send me an email. So for the next couple of weeks, given that I think over 3/4 of you now have passed your conversion quiz, we'll spend a little more time on lecture in the evening, a little less time on the quizzes. We'll still have the quiz for those that need to take it. Again, it's not a sprint. Just want you to get competent. So if you need to spend more time on it, you need to spend more time on it. Just keep learning. That's all I'm asking. Once we get everybody through that, what we'll do is we'll spend some time each week going through problems that are more hydrology and groundwater relevant. You'll use conversions, but now we'll start really getting into the science and using math to quantify some of the concepts we talk about. So that's kind of where we're going to go. And over the last few weeks, I've been punishing you with the chemistry and physics of water. That's going to change tonight. We're going to slide over and talk about things from a more geologic context, which I'm sure most of you will really enjoy and be happy that we're going to. But again, in this class, it's about concepts that are going to be related to the Earth, but it's also about quantifying those processes that we talk about. So that's where the math and the physics and the chemistry is going to come in. So you're going to end up with a blend of both through the whole semester. So let's just get started. I want to wrap up a couple things that were kind of left hanging from the last couple of weeks. So I talked about solids and liquids and gas. Solids, you have material that's bonded together. And since I think all of you are geologists, if you remember back to your definition of a mineral, who can remember most of the parts of the definition of a mineral? Any parts you remember?
Crystalline.
Crystalline. And what does crystalline mean?
It takes up a crystalline shape, so it has a repeating pattern.
It has a repeating pattern. Really good. What else?
It's consistently the same naturally occurring molecule.
Yeah. So
in a specific pattern.
H2O in a specific pattern. Crystalline means that there's long-range order to this thing. These things are bonded, again, millions and billions of times over.
And it also implies that it's a solid.
And it's a solid. Okay, so typically when a substance is a solid and has that nice geometric arrangement, that is the most efficient, tight, dense packing of material that you can get. So for the vast majority of substances, the solid is going to be the densest because it's forming the most efficient arrangement of atoms into geometric shapes. With water, that falls apart because you have a 105-degree angle. So as it turns out with water, your liquid is the most dense material. And as you freeze it, it becomes more open. And in fact, this is not the greatest diagram. It's making really nice hexagons here. In order to get nice hexagons, you have to have a 120-degree angle. Water, remember, is 105. So what it does is it makes crude hexagons, which would take up even more space than what we have there. And then if you change water into a gas from a liquid, it's the least dense of all materials. So again, remember, water, as it freezes, as it becomes a mineral, water is a mineral when it's in solid form. It tries to form those hexagons. It does a lousy job because it's not a molecule that has a 120-degree angle. It makes crude hexagons, and they just take up a lot of space, and for that reason, they become less dense. So the other thing that's really unique about water is how it changes with respect to energy. And we went through this exercise last week. And I just want to come back to it for a second and show it in a graphical form. Remember, we started with water at minus 20 degrees C. We heated it to 0 degrees C. We had 1 gram of material. And to do that, it required 20 calories. If you look at it as a graph, it's 1 calorie per every degree C that you want to raise the temperature of water of. Once you get to 0, though, so now you have solid at 0 degrees C. To move it to a liquid at 0 degrees C, you have to add in what's called latent heat of fusion, which was 80 calories per gram. And that's just to change it from a solid to a liquid without even raising the temperature. So on a graph, it might look something like this. Once you have a liquid at 0, to raise it to a liquid at 100 degrees requires 100 calories. So again, it might look something like this. To go from a liquid at 100 to a vapor at 100 requires latent heat of vaporization, which is a huge amount of energy, 540 calories. This obviously isn't drawn to scale, but it can look something like that. And then to raise it from gas at 100, vapor at 100, to vapor at 200 requires another 100 calories. So it's about 220 calories just to raise the temperature from minus 20 to 200 degrees C. 1 calorie for each degree C for every gram of water. But to change phase is about 620 calories. That's just to break the bonds between solids and liquids and vapors. So this is just another way of looking at the same thing that we talked about at the end of class last week. So again, not to scale, but I think you get the point. In other words, water requires a lot of energy to go through the phase changes. Boiling water is really difficult. When we talk about things like desalinating ocean water to get drinkable fresh water, that process involves boiling water. You boil the salt water, the salt remains behind, you capture the vapor, you cool it off, condense it back into freshwater liquid. Great process. Takes all the salt out of water. But it requires that latent heat of vaporization, which is a ridiculous amount of energy, which makes it a really expensive process. And that's one of the things that's holding back countries from being developed, is that they can't get enough fresh water. A lot of these countries sit on one of the oceans. They have this available potential supply of water if they can desalinate it, but the energy requirements are too great, too expensive, and it keeps a lot of places from developing and making a better place for the people that live there. Okay, so any questions on this? All right, let's talk about groundwater. I'm going to go through some basic terms, concepts that you may or may not have learned in previous classes. My guess is most of you have seen most of this, but I want to make sure again that everybody is on the same page. All right, so let's just start with a definition of groundwater. It's pretty simple. You can find different definitions in different textbooks, obviously. I always go for the simplest definitions in the most everyday terms if I can find them. Groundwater is simply water that resides in fractures and pore spaces beneath the Earth's surface. So basically, any molecule of water in the ground is considered groundwater. It can be what makes your soil damp. It can be water that you're pumping out of a well. It can be water that's found in a cave. Subsurface water of any type. So we're giving a big, broad definition for groundwater. Okay, there's a couple terms within that first definition that you probably know, but we're going to make sure. I said pore space. We use the term porosity a lot in this class. Porosity is the percentage of openings you can think of these as little holes between sand grains, perhaps, cracks in an igneous or metamorphic rock, any sort of opening where water can wiggle its way into. Typically, most of the rocks that we have here on Earth they range from 0% to maybe 30% pore space. One rock, pumice. I'm sure you guys have all seen pumice. Super lightweight because it's mostly pore space. It on average has around 77% porosity. It's rare to find a rock that much, but occasionally you can. Most of the rocks that we're going to talk about in this class, though, are going to be in this 0% to 30% range. The other term that's related, and that we also use a lot in this class, is something we call, make sure I keep my 1s and 2s and A's and B's consistent, permeability. A simple definition for permeability is the ability of a fluid or gas to move through a porous medium. Kind of simplifying it just for this class, you could think of it as the ability of water to flow through rocks and soils. Now, not all porous rocks are permeable. To be permeable, your water has to be able to move from pore to pore. So your pores have to be connected. So if you take something like pumice, if you take pumice and toss it onto water, it actually floats. The reason it floats is that the water can't get into all the pore spaces because those pores are not connected. Pumice actually has the highest permeability of any rock we know, or highest porosity, excuse me, of any rock we know, but a very low permeability because those gas bubbles are not connected. So I'll give you a couple examples here. I'm going to put the rock type here. The porosity here. And the relative permeability here. Now I'm just going to say here whether it's high permeability or low permeability. Later in the semester, we will attach a value to permeability. It's in a unit called Darcy's. We will use something called Darcy's law to mathematically track how material moves through pores. But that'll come later. So let's take something like a sandstone. I think you all have experience with sandstones. In sandstone, excuse me, in sandstones, the porosity comes from the spaces between sand grains because sand grains are rounded or irregular, they don't fit together perfectly, and they leave space in between. And typically the porosity for sandstone is pretty high. And when I say high, if you remember the values I gave you on the other page, it typically averages from 0 to 30. This is one of those that's up around 30%. So it has a high porosity. The other thing about those pores is that they are all very well connected. So water is very easily able to move from one pore to the next. So the permeability of a sandstone is very high. So in terms of groundwater, prospecting for groundwater, if you can find a sandstone that's saturated, that tends to be a very good aquifer because water can move and travel, and when you pump water out of the well, more water can come back in and replenish it because that's what you want. You want to be able to extract water from the ground, and you want that water to replenish itself as fast as you take it out. If you compare that, though, to an igneous rock, remember, igneous rocks formed by magma. When they cool, those crystals grow, lock together, and they leave very little pore space. So if you have sort of a pristine igneous rock that's been, let's say, unfractured by mountain building, you tend to have a very low porosity, somewhere around 2%. A stray gas bubble here or there, or a stray space between minerals in your cooled rock. Not only does it have very few pores, those pores are generally not connected at all. So your permeability is extremely low. Now shale, which is the most common rock type on continental surfaces. Okay, if you're on the continent, the most common rock is shale. There's lots of shale, especially east of here in the US, out on the prairie, Great Plains, lots of the rocks going down to the igneous basement rocks are shales. There are a lot of shales in the US. As it turns out, shales have a somewhat high porosity. They vary, but many of them are actually up around 20%. But what's interesting about shales is that the permeability is actually low, even though it's a fairly porous rock. And the reason is really twofold. One, the pores are poorly connected. Gotta get your right pore there. The other thing is that the pores tend to be too small. We talked last class that water has a high surface tension. And it's a polar molecule, so it sticks to charged surfaces. Lots of rocks have charged surfaces. So when your pores are really small, water has a hard time moving into them because the surface tension is too high to break and they're sticking to the sides of the rocks. So as it turns out, even though shale has some decent porosity, they have low permeabilities and tend to be really crappy aquifers. Okay, any questions so far? Again, for most of you, this is probably a review. All right, a third. Let me do that over. Color right. Next concept we'll bring up is something called the water table. I'm guessing most of you remember a fair bit about this from your physical geology or environmental geology class. To understand the water table, which is obviously a fundamental concept for groundwater, we're going to introduce some terms. First term is something called the unsaturated zone. You also hear it referred to as the vadose zone. And some books also call it the zone of aeration. You should know all the terms. When you read the literature and some textbooks, these terms are used by different folks in different ways. But for our purposes, when you're in the unsaturated zone, your pores are filled with both air and water. So the way I like to think about it is the unsaturated zone has three things. It's mostly rock. This is a rock layer. But it also has some water and some air. When we talk about pumping wells later in the semester, if you put a well into the unsaturated zone, a well is just a hole in the ground. That's all it is. And you start pumping, fancy word for sucking, when you start putting suction in this area, you have three things in the ground. You have rock, air, and water. Which of those three things moves the easiest? Air. You're going to suck air, and you're not going to have a functioning well. So you want to avoid putting your well into only the unsaturated zone, or you're going to suck air. It's a real expensive way of sucking air. The next term is something that we call the saturated zone. It's called the saturated zone because it's saturated with respect to water. In other words, the pores are filled only with water. So in this zone, again, it's mostly rock. But in a few percent to 30% of the rock, the openings, you're going to have water. If you put a well into this zone and start pumping, which of these two moves easiest, rock or the water? Water. Yay, you have a functioning well. So it's that simple. Also remember, and this is something we'll get into a bit later in the semester, remember water is incompressible. So when it's in the pores, it can't be squished. And remember, when you're in the ground, you're always going to have pressure from gravity pulling down all the overlying rock. So you can have quite a lot of pressure on these systems. But if there's water in the pores, then the water, because it can't be squished, actually acts as support for the rock. But if you somehow remove the water, if you suck the water out and replace it with air, air is very compressible. Now you don't have anything in the pores supporting the pores to keep them open. And over time, that pressure can slowly squeeze the pores shut and reduce your porosity. Once that happens, there's really no way to open them back up in the ground. So you may have had a situation where you had a nice porous and permeable rock, and then by pumping too much and sucking too much of the water out, replacing it with air, those pores can collapse, the porosity reduces, the permeability reduces, and you can go from a nice, functioning aquifer to a rock unit that won't give you any water at all. And that is a problem that is occurring in many parts of the United States today. The next term is related to both of these, and it's what we call the water table. There's really sort of three working definitions that you can use for the water table. One is it's the upper surface of the saturated zone. So you got to think about this in 3 dimensions, right? So you've got your unsaturated zone, which is going to be closest to the surface. At some point that transitions into the saturated zone, which is deeper down. The boundary between those areas are the water table, and in 3 dimensions you can think of it as being the upper surface of the saturated zone. You can also think of it as the boundary between the unsaturated and saturated zones. And from a practical standpoint, you can also think of it as the minimum depth required for a functioning well. So if we sort of draw this out, here's the Earth's surface. Near the surface is the unsaturated zone, which again is rock, water, and air. And then at some depth, the pores will completely fill, and you will end up in the saturated zone, where you have just rock and water. The boundary between these two zones is the water table. Now, the depths of the water table can vary according to a lot of different things. Out here in the West, it's not unusual for the water table to be thousands of feet beneath the surface. Typically hundreds of feet, but not unusual for it to be 1,000 feet or more. Drilling a well costs anywhere between $20 and $30 a foot. So if you have a 1,000-foot deep well, you're looking at $20,000 to $30,000 to put it in. Not insignificant. My dad lived in northern Wisconsin, and the water table there was about 6 feet. You could dig down to it with a shovel. And in fact, he couldn't have a basement, because the basement would have been in the saturated zone and would have been constantly filling with water, constantly having to pump it out with a sump pump. The minute the sump pump dies when you go on vacation, your whole basement's going to fill with water. So the people there didn't typically have basements. So it depends. Sometimes the saturated zone can intersect the Earth's surface. And when that happens, you get something called, do you guys know what it is? It's a spring. That's the definition of spring, is where the saturated zone hits the Earth's surface, water just basically pours out of the ground. Again, a couple things to remember. Remember, there is water in the unsaturated zone. There is water there. If you pump, you won't get it. You won't get it because this stuff moves easier. But there is water there. Actually, there can be quite a lot of water there. A couple things to think about. Let's say you spill gasoline on the Earth's surface and it soaks into the ground. Bummer, right? So it goes into the pore spaces, just like water would, right? So it's going to move around in the pore spaces. So it's going to take some sort of path. What happens when it hits the water table? It doesn't mix. So where does it go? Stay on the surface, or does it sink? You think it's just going to sort of spread out on top of the water table. Why that rather than sinking? You're right.
Chemical properties of water and oil are different.
They're different, and remember, oil tends to be less dense, so it'll tend to float on top. The other thing, if you've ever spilled gas on your driveway or some surface, even your hands, it evaporates pretty fast, doesn't it? That's why it feels so cold. If you put it on, if you spill it on your driveway, it evaporates really quick. So it has to have air to evaporate into, right? Does this gas have air to evaporate into? In the pores, right? So what will happen is this stuff will sort of volatilize, it'll evaporate and go into the pores in the rock and soil, which makes it almost impossible to clean it up. How do you clean that up?
Take the entire mass of soil and move it.
That happens a lot where if you get leaky gas tanks at a gas station, they'll end up digging up the soil in a whole area and trucking it off to the landfill and bringing in new stuff. That is not cheap. There are companies that are trying to develop aeration systems, basically blowing air into the ground to move this stuff back out. They've had limited success with it, but in places where digging up all the soil isn't practical, that could be an option. And those companies tend to make an awful lot of money because they're the last resort for a lot of people that have polluted the area. So just a few sort of things to think about in relation to the unsaturated zone, saturated zone, water table. All right, any questions?
Is that gas that would leak into the soil floor, is that combustible?
Yeah,
Yeah. So it can just, it's spontaneous combust?
it can burn, yes. Yeah. There's not a lot of, in order to get burning, you have to have oxygen, right? And remember, there's not a lot of pore space in here. So what will happen is sometimes it will ignite, but then it just sort of smolders because it's not getting enough air. Not so common with this, but it happens a lot with coal seams. And it's happened a lot here in the western US. What can happen is if you get a coal seam that intersects the Earth's surface but plunges into the ground, over time, lightning may strike an area and can actually strike the coal seam and it can catch on fire. And it burns like crazy while it's on the surface and it starts to burn the coal underground, but then has less oxygen surrounding it to keep burning, and it just smolders. There are fires. There's a fire in, if I remember right, in Centralia, Pennsylvania, that's been burning for over 100 years. It's still burning. It's still burning today. It just smolders and they can't really put it out. I was driving from Laramie to Steamboat Springs last weekend, going through the scar of the Mullen Fire, one of the big fires that we had this summer. It's still burning. It gets covered by the snow, the oxygen reduces, but it just smolders there. And it's still smoldering in places. You go through and you can see smoke where the snow has finally melted away, and you get some oxygen and you get little flare-ups. They're still getting flare-ups from that fire. So it's kind of related to the same process as we have here. To have fire, you have to have oxygen. You have limited oxygen in this area, but these things can ignite and they can smolder for some time. Okay, any other questions on this? All right, let's do one more little bit and we'll take a break. All right, let's look at, get my colors right. Let's talk about the movement of groundwater. So groundwater moves in response to two main things. One is changes in pressure. It'll move from areas of high pressure towards areas of lower pressure, just like most movable substances. And it flows in response to gravity. Water movement is typically pretty slow in the ground. The range of speeds is pretty variable, but it can range from, say, less than a centimeter a year. Write that a little better. And that would be in a rock such as a shale. But in the right environments, it can move hundreds of meters per day. In something like, say, loose sand along a river. Typically, we're talking about centimeters to meters per day. Kind of glacial, you know? Another thing is that the water table tends to mimic the topography. So if you have a surface that's sort of undulating like this, then the water table is going to tend to mimic that overlying surface. If your area is flat and has no slope, the water table beneath will tend to be flat and probably have no slope. If you're on a steep slope, the water table beneath the ground is probably going to be steeply dipping as well. So whatever the surface is doing, the water table is going to follow it to some degree. It might not be perfect, but in general it's going to mimic what you have above it. Okay, let's take a 10-minute break and we'll do a little more.